In the last video, we considered the Eisenstein criterion, which is a good way of measuring checking whether a polynomial, integer polynomial is reducible either over the rationals or the integers. And we also did some problems on how to use it. It's not always applicable, but when it's applicable, it's a very easy way of determining irreducibility. So that completes the topic of ring theory that I wanted to cover in this course. But before moving to the next topic, which is fields, let me do a few problems on rings in general on many of the topics that we covered in this last few weeks. So let me solve some problems in today's video. Some of this I may have referred to in some earlier videos, but let me do it anyway again. So let R be a ring. We know that this is really more, not just a problem, but I am defining a new thing and we will compute it for some examples. So we know that there is a unique, this is very important, unique ring homomorphism phi from Z to R. Z, remember, always represents the ring of integers. There is a unique ring homomorphism. Remember that phi of 1 must be 1. For us, ring homomorphism by definition sends the unit multiplicative identity to the multiplicative identity. And once you insist on that, there is exactly one ring homomorphism, right? Because once you know that 1 has to go to 1, 2 has to go to 2, minus 2 has to go to minus 2, minus 1 has to go to minus 1, and so on. So that we have discussed earlier. There is a unique ring homomorphism. So consider the kernel of this ring homomorphism. We know that any ideal, kernel is an ideal of the integers, any ideal of the ring of integers is of the form nz for some non-negative integer, right? N is a non-negative integer. So we define the characteristic. So this is an important word in ring and field theory. Characteristic of R, which I denote usually by just CHAR bracket R, is N. Okay, so that's all. So characteristic of R is equal to the generator, the non-negative generator of the kernel of the unique map from Z to R. So as an example, what is the characteristic of Z? What is the characteristic of Z? Remember, there is a unique map from Z to Z. In fact, that's the identity map, identity ring homomorphism. Its kernel is the 0 ideal because it's an injective map, and hence the generator is 0. So characteristic of Z is 0, and that actually also is the characteristic of Zx, polynomial ring in any number of variables. This is the characteristic of Q, characteristic of R, and so on. So characteristic of C. All these rings have the unique map from the ring of integers to these rings is injective. That means characteristic is 0. The generator of the kernel is 0. Similarly, we know that if characteristic, this is covered here, but if characteristic of R is, okay, so maybe I will postpone this, I can just say this, I guess. If characteristic of R is N, then characteristic of the polynomial ring over R is also, let's say this is M or some other number of variables, so xm, then this is also N, right? Because if there is the ring homomorphism, the unique ring homomorphism from this is injective. The inclusion of R in the polynomial ring is injective. So the unique ring homomorphism from Z to the polynomial ring is simply the composition of the unique ring homomorphism from Z to R and then followed by the inclusion, because 1 has to go to 1. So this is there is only one map from Z to the polynomial ring. It must be the composition of these two because that's a map from Z to that. So this is the unique map. And once you have this unique map, because R to R adjoined x1 through xn is injective, kernels are same. Kernel of the map from Z to the polynomial ring is equal to the kernel of the map from Z to R, because if something goes to 0 under the composition, it must go to 0 in the first map itself, because second map is injective. So the characteristic does not change if you simply add some more variables, or in general, if R more generally, the same principle actually says that if R is a subring of S, if let's say R is a subring of R prime, and then characteristic of R is same as characteristic of R prime, because there is a unique map from Z to R, there is a unique map from Z to R prime, which must be the composition of the map from Z to R and the inclusion of R and R prime. So these are easy observations, and we can also say characteristic of Z mod NZ is N, right? So this is because the reason is the unique map from Z to Z mod NZ has kernel NZ, right? So the reason is that the unique map from Z to Z mod NZ has kernel NZ. So the characteristic of Z mod NZ is N. So in other words, for every non-negative integer N, there exists a ring of characteristic N. Okay, this is an easy observation, because you can simply take Z mod NZ. So we have not yet gotten to the problem, but the problem now I will ask is, show that if R is an integral domain, then characteristic of R is either 0 or characteristic of R is a prime number. Remember, characteristic is always a non-negative integer. So for an integral domain, it cannot be any arbitrary non-negative integer. It has to be either a prime number or it has to be 0. So 0 is also allowed, and the reason is solution. So consider the unique map or the unique ring homomorphism from Z to R, and let kernel of this phi be NZ. So by the first isomorphism theorem, we have an injective map which I will denote by also phi from Z mod NZ to R, right? This is an injective map. So Z mod NZ is isomorphic to a subring of R. Now we are given that since R is an integral domain, so I will shorten it like this. Since R is an integral domain, so is Z mod NZ, right? We know very well that if you have an integral domain, a subring is also an integral domain. That's very easy to show, because what is an integral domain? Product of two non-zero things is non-zero. But if R is a subring, if Z mod NZ is a subring of R, you take two things in Z mod NZ, they are also inside R, and there if they are both non-zero, their product is non-zero in R. So it's also non-zero in Z mod NZ because it's a subring. But then if Z mod NZ is an integral domain, which is what we just concluded, this implies that n is 0 or n is prime, right? This is something that I discussed when I talked about integral domains. The quotient ring Z mod NZ is an integral domain only if n is 0 or n is a prime number. For example, Z mod 4Z is not an integral domain because 4 is not prime and 4 is not 0. There you can get 2 bar times 2 bar is 0. So this we did earlier. So I will not do this again, but this shows that characteristic of an integral domain is either 0 or it's prime. Okay. So now on the other hand, so this solves it, right? But converse is not true. What I mean is, if the characteristic is prime or characteristic is 0, it need not be an integral domain. For example, you consider R to be Zx, Y, let's say, modulo the element polynomial xy. So what is the characteristic of R? Characteristic of R is 0. This I will leave as an exercise. The point is Z is a subring of this, right? Because constant can be viewed as subring of Zxy for sure, and then you are killing xy, so you are not killing any integer. So Z continues to be a subring of R. But is R an integral domain? Of course not. R is not an integral domain, right? Because x bar and y bar are non-zero, but x bar y bar is 0, right? We have killed x y, so x bar y bar is 0. Similarly, if you take R prime to be z mod 2z, let's say, or z mod 11z x mod x squared, characteristic of R prime is actually 11, because this is also an exercise. Z mod 11z sits inside this as a subring, but R prime is not an integral domain for the same reason, right? Because x bar is non-zero, but x bar squared is 0. Okay, so characteristic of an integral domain is always either 0 or a prime number, but if a ring has characteristic 0 or a prime number, does not mean that ring is an integral domain. Okay, so before I continue to the next problem, let me basically make a remark that if characteristic of R is n, then if you take one R and add, so suppose n is not 0, assume that characteristic of R is an integer n not 0, then if you add n n times, you get 0, right? Because that means if you, under this assumption, z mod nz sits inside as a subring of R. Okay, so actually let me do it like this. Z to R there is a map, kernel is n, that means n is contained in the kernel, so phi of n is 0. But what is phi of n? Phi of n is 1R plus 1R plus 1R, that is 0. Okay, so that is the reason for this. And not just that, moreover, 1 plus 1 plus 1, if you take m less than n times, it is not 0. So n is the least positive integer such that 1 times 1 times 1 plus 1 plus 1 plus 1 n times is 0. In other words, anything smaller it will not work. On the other hand, if characteristic is 0, 1 plus 1 plus 1 any number of times is not 0, is never 0, right? Because the map from, in this case, the map from Z to R is injective by definition, because if the characteristic is 0, kernel is 0, that means it's an injective map. So when you take phi of n, it is non-zero, phi of any number is non-zero, that means 1 plus 1 plus 1 any finitely many times, it is not 0. Okay, so that is never 0. So this is one good way of keeping track of characteristic of a ring. So now let me do a second problem here, which is actually a good way to combine group theory and ring theory, group theory that you learned in the past, and it is somewhat confusing actually if you think about it, if you are seeing this for the first time, but let's do this carefully. Let us consider Z mod nz be the additive group. So of course Z mod nz is also a ring, so that means we are only considering the additive group structure. So fix any positive, any non-negative integer, consider, so fix an non-negative integer n, we are only considering the additive group structure. For now we are only considering the additive group structure of Z mod nz. Okay, so let's take this. I am interested in the following object. So this is called endomorphism set for now. So these are group homomorphisms from G to G. Okay, so let us denote this by end of G. This is by definition all group homomorphisms from. So let me emphasize again, phi is just a group homomorphism. Z mod nz is also a ring, but I am not looking at ring homomorphisms. That means I am not insisting that 1 goes to 1. So we do get lots of new objects, because if you insist on if you only consider ring homomorphism, then there is exactly 1, because 1 has to go to 1. There is only one element in the set of ring homomorphisms. Now I am considering only the set of group homomorphisms, so there are more elements. So first show that, so the first part of the problem is show that Ng is actually a ring. Okay, the solution for this is very easy. I will not do all the details because I want to do some other problems also. So let me set this up and leave the actual verifications to you. This part is easy. Show that Ng is a ring. So what do we do? So let's first of all 0 is there. What is 0? It is, so I'll just denote by 0. It's the map from G to G, sending every element to 0. So remember, G is an additive group. It has an additive identity, which we usually call 0. So sends everything to 0. 1 in Ng, I claim, is the identity map. Okay, this will make sense once we actually define addition and multiplication. Is the identity map. That means it sends small x to small x. And what is addition? So maybe I should have said this first. If you take phi 1, phi 2 in Ng, what do we do? Phi 1 plus phi 2 must be another element of Ng, right? That means it must be a homomorphism from G to G. And what is that? I will simply define phi 1 plus phi 2 of x. I will simply add in G. So phi 1 plus phi 2 of x will be phi 1x plus phi 2x. So this is the addition in Ng. What is multiplication? Multiplication is simply composition. Composition of two functions. Because phi 1, phi 2 are both functions from G to G, right? Phi 1 is from G to G, phi 2 is also from G to G. These are actually group homomorphisms. I define phi 1, phi 2 of x to be phi 1 of phi 2 of x. This is the multiplication. In Ng. Right, so in order to show that Ng is a ring, we need to say what is addition, what is multiplication. Addition is defined here by adding in the target group. Multiplication is defined to be composition. So what I will leave for you to check is, with these operations, Ng is actually a ring. In fact, it is a commutative ring. We remember all our rings are supposed to be commutative with unity. We know that it has a unity because remember 1 is defined to be the identity map. So when you multiply any endomorphism with 1, that means you are composing any endomorphism with the identity map, you get that endomorphism back. So 1 is identity, it is actually commutative. So this is the tricky part. in general, composition is not commutative, right? You can compose two functions f and g, and in either f circle g or g circle f. In general, they are different, but in this specific example, it's commutative. So commutativity is something you have to check. The other conditions are fairly straightforward, because if phi1 and phi2 are group homomorphisms, their sum is group homomorphism. If phi1, phi2 are group homomorphism, their composition is also group homomorphism. These are all group theoretic properties that one has to check. Phi1 plus 0 is phi1, phi1 circle phi2 is equal to phi2 circle phi1, that I told you to check. Phi1 circle 1 is phi1, and you have to check distributive property. You have to check that under addition it's a group. That is clear because phi1 has an inverse, right? Minus phi1. Minus phi1 sends x2 minus phi x, minus phi1 of x. So that's the additive inverse. Not everything will have a multiplicative inverse, but that's not required for us. So this I will leave for you to check. So check this. So even though this is a video on problems, I will not do that because that's a fairly straightforward exercise. The second exercise is to show that now that by first exercise we know that end G is a ring. What kind of ring is it? We show that end G is isomorphic to Z mod NZ as rings. That means there is a ring isomorphism from let me reverse the direction, doesn't matter. So there is a ring isomorphism from Z mod NZ to end G. So that means so this is the tricky part of this. What I have started with is Z mod NZ is considered as a group only, not as a ring. I consider the set of all homomorphisms, all group homomorphisms from G to G. That actually inherits a ring structure, and as a ring it is isomorphic to Z mod NZ. Now Z mod NZ is being considered as a ring. Okay, so you have to keep track of various notations here, and Z mod NZ is appearing in several roles. First as a group, now as a ring. So I'm going to simply define an isomorphism and define a map and show that it's isomorphism. So for A in Z mod NZ, consider the map phi A, which is from G to G. Consider the group homomorphism. I should write. Consider the group homomorphism from G to G determined by A. What is this? Okay, so this is given by phi A of x is Ax. So now I need to tell you what is Ax. Remember Z mod NZ, one way of representing elements of Z mod NZ is this. So we are implicitly using the multiplication in Z mod NZ, right? Because though it's actually a group, but because it's coming from integers, multiplication is actually just addition. So when I write, for example, if you take Z mod 6Z, it will be 0 bar, 1 bar to 5 bar. Let's say A is 3 bar and X is 4 bar. What is A times X? It is 3 bar times 4 bar, which is really 4 bar plus 4 bar plus 4 bar, because 3 bar serves as the number 3 in this ring. So multiplying by 3 means it's adding 4 bar 3 times to itself. This is 12 bar, which is actually 0 bar. So this is an example. So we can always make sense of A times X is really X plus X plus X A times, where A is an element of G, so it's not an integer, but it has a representative in the ring of integers. Now if you take another representative, Ax does not change. For example, here you can take 3 bar, but 3 bar is also 9 bar, right? So 3 bar is equal to 9 bar. So I can also do 9 times 4 bar, which is 36 bar, which is 0 bar. So because we are going modulo n at the end, what integer I choose to represent A is irrelevant. I can choose any integer that represents A and multiply by that. So I claim that, in fact I wrote this here, but one has to check that it is in fact a group homomorphism. Claim phi A is a group homomorphism. This is very easy to check because this is easy. Phi A of x plus y is A times x plus y, which is Ax plus Ay, which is of course phi A of x plus phi A of y. Similarly, phi A of 0 is A times 0, which is 0. So this is why it is a group homomorphism. That means phi A is in end G. Remember what is our notation for end G? These are group homomorphisms from G to G. So phi A is one such, so it's in end G. Now define the map capital phi from Z mod nz to end G. Remember in the previous slide we started with an arbitrary element A and defined a endomorphism phi sub A. Now I am defining capital phi by defining capital phi of A is simply phi A. We have already checked in the previous slide that phi A lands in end G. So capital phi of A is small phi sub A. So now we claim that capital phi is a ring homomorphism. So now we are in the realm of rings and ring homomorphisms. So we want to now show that it is a ring homomorphism. Small phi A is a group homomorphism, right? Now capital phi is a ring homomorphism. So in particular we want to now show that phi of 1 is 1. Why is this? What is phi of 1? So I am proving this now. Phi of 1 is phi small phi sub 1. And what is small phi sub 1? It is a ring homomorphism from G to G. And what does it do? Phi sub 1 of x is 1 times x, which is x. Right? That means phi sub 1 is the identity map. Hence, phi sub 1 is the identity element in end G as required. So capital phi of 1 is equal to 1. When I write 1 in the bracket here represents 1 in Z mod nz. On the right hand side 1 represents the identity endomorphism. So we check that. What is phi of, let's take phi sub A, phi of A plus B should equal phi of A. So that's done. The first part is done. The next part is to show the additive homomorphism structure. Capital phi of A plus B is capital phi A plus capital phi B. What is this? So let's check both of these sides. This is an equality of what? This is an equality in end G, right? That means this is an equality of maps of, that is, of maps. Right? So we are supposed to check that these are same maps on G. So let's take an X. So of course before that, let me first note that what is phi of A plus B? By definition it is small phi sub A plus B. So now, and this is small phi sub A and this is small phi sub B. So we want to check that small phi sub A plus B is equal to small phi sub A plus small phi sub B. So let us take an arbitrary element of G and compute both sides. What is a phi sub A plus B of x? This is A plus B times x. This is Ax, because remember A is really being thought of as an integer, but Ax plus Bx is actually phi sub Ax, phi sub Bx. This, by the definition of addition in end G, this is actually phi sub A plus phi sub B of x, because when you add to endomorphisms, you just add it in the, take the image and add. So this is what we require. So this is checked. Now finally, we have to check that phi of AB is equal to phi of A times phi of B. So what is this? This is phi of A, small phi sub A B, this is small phi sub A, this is small phi sub B, and what is the product in end G? This is actually composition. We want to check this. So the third condition is this. I'll write it as, maybe I'll just put a dot here. Second condition is this, first condition is this. So let's check now. This is also an equality of maps of G to G. So let us take an arbitrary element x in G. What is phi AB of x? This is AB times x by definition. This is A times B of x because of the associativity of multiplication. But this is A times phi B of x, which is phi A of phi B of x, which is by definition phi A composed with phi B of x as required, right? So this is exactly the required equality. So on every x they agree. So this holds also. So capital phi is a ring isomorphism. Okay, that's good. Ring homomorphism, not yet a ring isomorphism. Now the remaining thing is to check that it is in fact a ring homomorphism. It is also an isomorphism. How do you verify that a given ring homomorphism is an isomorphism? All we need to show is that it is bijective. Capital phi is bijective. But this is easy because it's also a ring homomorphism, already a ring homomorphism. We will first check that it's injective. So capital phi is injective. Why? What is kernel? Suppose A belongs to, remember capital phi again, let me remind you, is a map from Z mod NZ to end G. Suppose A belongs to kernel of phi. So to prove that a ring homomorphism is injective, it suffices to show that kernel of that ring homomorphism is 0. So if A belongs to kernel of capital phi, that means capital phi A is 0. That means phi sub A is 0 as a map of from G to G. So phi sub A of 1 is 0. That means A times 1 is 0. That means A is 0. So phi is injective. Now phi is an injective map from phi is injective from so what is it? Yeah, phi is injective that we have shown. Now what is it that we have to show now? Phi is surjective. We are trying to show that it's bijective, so we have shown it's injective, so we have to show it's surjective. So for this part, let us take an arbitrary endomorphism of the group G. This is a group homomorphism from G to G. Then we claim, I will not prove this. So suppose, before I write the claim, so let A be phi of 1. Remember phi is a group homomorphism from G to G. So I am simply taking phi of 1 to be A. So let us take A to be 1. The point is A now determines the entire group homomorphism phi. So the claim is phi is actually equal to phi sub A, which is capital phi of A. Because why? The reason is phi of x is actually A times phi 1. Sorry, x times phi 1, which is Ax. But this is also same as phi A of x. Okay, so the whole point is to show that phi of x is x times phi 1, and that is because x can be written as 1 plus 1 plus 1 x times. So because phi is a group homomorphism, phi of x is phi of 1 plus 1 plus 1, and you can now do phi of 1 plus phi of 1 plus phi of 1 x times, which is exactly this. So this part, if it's not clear, just think about it for a few minutes and it will become clear to you. So this shows that phi is a surjective map, it is an injective map, and it is a homomorphism as we verified here. So the conclusion is these are isomorphic as rings. So this is a very nice problem because it now combines everything that you know about groups and rings, and it allows you to see everything in its proper place. So if you carefully follow this video and understand this problem solution, it will be useful to you in understanding ring theory. I'm going to stop this video here. In the next video, we will do some more problems. Thank you.